So far, we've been talking about SVMs at a fairly abstract level. In this video, I'd like to talk about what you actually need to do in order to run or to use an SVM. The support vector machine algorithm poses a particular optimization problem, but as I briefly mentioned in an earlier video, I really do not recommend writing your own software to solve for the parameters data yourself. So just as today, very few of us, or maybe almost essentially none of us, would think of writing code ourselves to invert a matrix or take the square root of a number and so on. You just call some library function to do that. In the same way, the software for solving the SVM optimization problem is very complex, and there have been researchers that have been doing essentially numerical optimization research for many years to come up with good software libraries and good software packages to do this. And I strongly recommend just using one of the highly optimized software libraries rather than trying to implement something yourself. And there are lots of good software libraries out there. The two that I happen to use the most often are liblinear and libsvm, but there are really lots of good software libraries for doing this that you can link to many of the major programming languages that you may be using to code up learning algorithm. Even though you shouldn't be writing your own SVM optimization software, there are a few things you need to do though. First is to come up with some choice of the parameter C. We talked a little bit about the bias variance properties of this in an earlier video. Second, you also need to choose the kernel or the similarity function that you want to use. So one choice might be if you decide not to use any kernel, and the idea of no kernel is also called a linear kernel. So if someone says, I use an SVM with a linear kernel, what that means is they use an SVM without using a kernel, and it was a version of the SVM that just uses theta transpose things, right? That predicts 1 if theta 0 plus theta 1 x1 plus so on plus theta n xn is greater than or equal to 0. And this term linear kernel, you can think of this as, this is a version of the SVM that just gets you a standard linear classifier. So that would be one reasonable choice for some problems, and there would be many software libraries like liblinear was one example out of many. Is one example of a software library that can train an SVM without using a kernel, also called a linear kernel. So when would you want to do this? Well, if you have a large number of features, if n is large, and m, the number of training examples, is small, then you have a huge number of features. If this is an x is in Rn or Rn plus 1. So if you have a huge number of features already, with a small training set, maybe you want to just fit a linear decision boundary and not try to fit a very complicated nonlinear function, because you might not have enough data and you might risk overfitting if you're trying to fit a very complicated function in a very high dimensional feature space, but if your training set is small. So this would be one reasonable setting where you might decide to just not use a kernel, or equivalent to use what's called a linear kernel. A second choice for the kernel that you might make is this Gaussian kernel, and this is what we had previously. And if you do this, then the other choice you need to make is to choose this parameter sigma squared, when we also talk a little bit about the bias variance trade-offs of how if sigma squared is large, then you tend to have a higher bias, lower variance classifier. But if sigma squared is small, then you have a higher variance, lower bias classifier. So when might you choose the Gaussian kernel? Well, if your original features x are in Rn, and if n is small, and ideally, if m is large, right? So that's if we have, say, a two-dimensional training set, like the example I drew earlier. So n is equal to 2, but we have a pretty large training set. So I've drawn in a fairly large number of training examples. Then maybe you want to use a kernel to fit a more complex nonlinear decision boundary, and the Gaussian kernel would be a fine way to do this. I'll say more towards the end of the video, a little bit more about when you might choose a linear kernel or a Gaussian kernel and so on. But concretely, if you decide to use a Gaussian kernel, then here's what you need to do. Depending on what support vector machine software package you use, it may ask you to implement a kernel function or to implement the similarity function. So if you're using an Octave or MATLAB implementation of an SVM, it may ask you to provide a function to compute a particular feature of the kernel. So this is really computing f subscript I for one particular value of I, where f here is just a single real number, right? So maybe this is better written fi. But what you need to do is write a kernel function that takes as input, a training example or a test example, whatever. It takes in some vector x and takes as input one of the landmarks, and but only I'm calling them x1 and x2 here because the landmarks are really training examples as well. But what you need to do is write software that takes as input, x1, x2, and computes this sort of similarity function between them and return a real number. And so what some support vector machine packages will do is expect you to provide this kernel function that takes as input, x1, x2, and returns a real number, and then it will take it from there, and it will automatically generate all the features. So automatically, take x and map it to f1, f2, down to fm using this function that you write, and generate all the features and train the support vector machine from there. But sometimes you do need to provide this function yourself. Although if you're using the Gaussian kernel, some SVM implementations will also include the Gaussian kernel and a few other kernels as well, since the Gaussian kernel is probably the most common kernel. Gaussian and the linear kernels are really the two most popular kernels by far. Just one implementational note: if you have features on very different scales, it is important to perform feature scaling before using the Gaussian kernel. And here's why. If you imagine computing the norm between x and L, right? So this term here is sort of like the numerator term over there. What this is doing, the norm between x and L, that's really saying, let's compute a vector v, which is equal to x minus L, and then let's compute, right, the norm of this vector v, which is the difference between x and L. And so the norm of v is really equal to v1 squared plus v2 squared plus dot 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 plus vn squared, because here x is in Rn or Rn plus 1, but I'm going to ignore x0. So let's pretend x is in Rn and put a square on the left side as well to make this correct. And so this is equal to that, right? And so written differently, this is going to be x1 minus L1 squared plus x2 minus L2 squared plus dot 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 plus xn minus Ln squared. And now if your features take on very different ranges of values, so take our housing prediction example, you're trying to if your data is some data about houses, and if x is in the range of thousands of square feet, right, but for the first feature x1, but if your second feature x2 is the number of bedrooms, so if this is in the range of 1 to 5 bedrooms, then x1 minus L1 is going to be huge. This could be like 1,000 squared, whereas x2 minus L2 is going to be much smaller. And if that's the case, then in this term, those distances will be almost essentially dominated by the sizes of the houses, and the number of bedrooms will be largely ignored. And so to avoid this, in order to make an SVM work well, perform feature scaling, and that will make sure that the SVM gives comparable amount of attention to all of your different features, and not just to, in this example, the size of the houses while ignoring the other features. When you're applying a support vector machine, chances are by far the two most common kernels you use will be the linear kernel, meaning no kernel, or the Gaussian kernel that we talked about. And just one note of warning, which is that not all similarity functions you might come up with are valid kernels. And the Gaussian kernel and the linear kernel and other kernels that sometimes others will use, all of them need to satisfy a technical condition. It's called Mercer's theorem. And the reason they need to do this is because support vector machine algorithms or implementations of the SVM have lots of clever numerical optimization tricks in order to solve for the parameters theta efficiently. And in the original design of SVMs, there was a decision made to restrict our attention only to kernels that satisfy this technical condition called Mercer's theorem. And what that does is that makes sure that all of these SVM packages, all of these SVM software packages, can use a large class of optimizations and get the parameter theta very quickly. So what most people end up doing is using either the linear or the Gaussian kernel. But there are a few other kernels that also satisfy Mercer's theorem and that you may run across other people using, although I personally end up using other kernels, very, very rarely, if at all. Just to mention some of the other kernels that you may run across, one is the polynomial kernel. And for that, the similarity between x and L is defined as, there are a lot of options, I guess. You can take x transpose L squared. So, here's one measure of how similar x and L are, right? If x and L are very close to each other, then the inner product will tend to be large. And so, this is a slightly unusual kernel that's not used that often, but it works. That you may run across it. So there's some people using it. This is one version of the polynomial kernel. Another is x transpose L cubed, or these are all examples of the polynomial kernel. X transpose L plus 1 cubed, x transpose L plus maybe a number different than 1, like 5, and then to the power of 4. And so the polynomial kernel actually has two parameters. One is what number do you add over here? And it could be 0. This is really hat plus 0 over there. As well as what's the degree of the polynomial. So the degree, the power, and this number. So the more general form of this, of the polynomial kernel, is x transpose L plus some constant, and then to some degree in the exponent. And so both of these are parameters for the polynomial kernel. So the polynomial kernel almost always or usually performs worse than the Gaussian kernel and is not used that much, but it's just something that you may run across. Usually it's used only for data where x and L are all strictly non-negative, and so that ensures that these inner products are never negative. But it captures this intuition that if x and L are very similar to each other, then maybe the inner product between them will be large. But it has some other properties as well, but people then tend not to use it much. And then depending on what you're doing, there are other sort of more esoteric kernels as well that you may come across. There's a string kernel. This is sometimes used if your input data is text strings or other types of strings. There are things like the chi-squared kernel, the histogram section kernel, and so on. There's sort of more esoteric kernels that you can use to measure similarity between different objects. So, for example, if you're trying to do some sort of text classification problem where the input x is a string, then maybe you want to define the similarity between two strings using the string kernel. But I personally, end up very rarely, if at all, using these more esoteric kernels. I think I might have used the chi-squared kernel maybe once in my life, and the histogram kernel maybe once or twice in my life. And I've actually never used the string kernel myself. But in case you run across this in other applications, if you do a quick web search, if you do a quick Google search or a quick Bing search, you should find definitions of these other kernels as well. So, just two last details I want to talk about in this video. One is multi-class classification. So if you have 4 classes, or more generally k classes, how do you get an SVM to output some appropriate decision boundary between your multiple classes? Many SVM packages already have built-in multi-class classification functionality. So if you're using a package like that, you just use that built-in functionality, and that should work fine. Otherwise, one way to do this is to use the one versus all method that we talked about when we were developing logistic regression. So what you do is you train k SVMs if you have k classes, one to distinguish each of the classes from the rest, and this will give you k parameter vectors. So this will give you, theta 1, which is trying to distinguish class y equals 1 from all of the other classes. Then you get a separate parameter vector theta 2, which is what you get when you have y equals 2 as a positive class and all the others as a negative class, and so on, up to a parameter vector theta k, which is the parameter vector for distinguishing the final class k from everything else. And then lastly, this is exactly the same as the one versus all method we have for logistic regression. Really, you just predict the class I with the largest theta I transpose x. So that's multi-class classification of SVMs. But the more common case is that there's a good chance that whatever software package you use, there'll be a reasonable chance that it'll already have built-in multi-class classification functionality, and so you don't even need to worry about this yourself. Finally, we developed support vector machines starting off with logistic regression and then modifying the cost function a little bit. So the last thing I want to do in this video is just say a little bit about when you would use one of these two algorithms. So let's say n is the number of features and m is the number of training examples. So when should we use one algorithm versus the other? Well, if n is large relative to your training set size, so for example, if you think of this as if the number of features is much larger than m. And this might be, for example, if you have a text classification problem where the dimension of your feature vectors, I don't know, maybe 10,000, and if your training set size is maybe 10, maybe up to 1,000, right? So imagine a spam classification problem where email spam, where you have 10,000 features corresponding to 10,000 words, but you have, maybe 10 training examples or maybe up to 1,000 examples. So if n is large relative to m, then what I would usually do is use logistic regression or use an SVM without a kernel, or use it with a linear kernel. Because if you have so many features but a smaller training set, a linear function will probably do fine, and you don't have really enough data to fit a very complicated nonlinear function. Now, if n is small and m is intermediate, so what I mean by this, if n is maybe anywhere from 1 to 1,000, 1 would be very small, but maybe up to 1,000 features, and if the number of training examples is maybe anywhere from 10 to maybe up to 10,000 examples, maybe up to 50,000 examples. So if m is pretty big, like maybe 10,000, but not a million, right? So if m is intermediate size, then often an SVM with a linear kernel will work well. We talked about this earlier as well, but one concrete example of this would be if you have a two-dimensional training set. So if n is equal to 2, but you have, drawing in a pretty large number of training examples, so Gaussian kernel would do a pretty good job separating positive and negative clauses. One third setting that's of interest is if n is small, but m is large. So if n is, again, maybe 1 to 1,000, could be larger, but if m was, maybe 50,000 and greater to millions, right? So 50,000, 100,000, million, 2 million, you can have very, very large training set sizes, right? So if this is the case, then an SVM with a Gaussian kernel will be somewhat slow to run. Today's SVM packages, if you're using a Gaussian kernel, tend to struggle a bit. If you have, maybe 50,000 is okay, but if you have a million training examples, or maybe even 100,000, with a massive value of m, today's SVM packages are very good, but they can still struggle a little bit when you have a massive training set size and you're using a Gaussian kernel. So in that case, what I would usually do is try to just manually create or add more features, and then use logistic regression or an SVM without a kernel. And in case you look at this slide and you see logistic regression or SVM without a kernel, in both of these places, I kind of paired them together. Well, there's a reason for that, is that logistic regression and SVM without a kernel, those are really pretty similar algorithms, and either logistic regression or SVM without a kernel will usually do pretty similar things and give pretty similar performance, but depending on your implementational details, one may be more efficient than the other. But where one of these algorithms applies, logistic regression or SVM without a kernel, the other one is likely to work pretty well as well. But a lot of the power of the SVM is when you use different kernels to learn complex nonlinear functions. And this regime, when you have maybe up to 10,000 examples, maybe up to 50,000, and your number of features is reasonably large, maybe that's a very common regime, and maybe that's a regime where a support vector machine with a Gaussian kernel will shine and can do things that are much harder to do than with logistic regression. And finally, where do neural networks fit in? Well, for all of these problems, for all of these different regimes, a neural network or well-designed neural network is likely to work well as well. The one disadvantage, and one reason I might not sometimes use a neural network, is that for some of these problems, the neural network might be slower to train. But if you have a very good SVM implementation package, that could run faster, quite a bit faster than your neural network. And although we didn't show this earlier, it turns out that the optimization problem that the SVM has is a convex optimization problem. And so the good SVM optimization software packages will always find the global minimum or something close to it. And so for the SVM, you don't need to worry about local optima. In practice, local optima aren't a huge problem for neural networks, but they also, it's just one less thing to worry about if you're using an SVM. And depending on your problem, the neural network may be slower, especially in this sort of regime, than the SVM. In case the guidelines they gave here seem a little bit vague, and if you're looking at some problems and you still feel like, the guidelines are a bit vague, I'm still not entirely sure, should I use this algorithm or that algorithm? That's actually okay. When I face a machine learning problem, sometimes it's actually just not clear what is the best algorithm to use. But as we saw in earlier videos, really, the algorithm does matter, but what often matters even more is things like how much data do you have, and how skilled are you, how good are you at doing error analysis and debugging learning algorithms, figuring out how to design new features, or figuring out what other features to give your learning algorithm and so on. And often those things will matter more than, are you using a logistic regression or an SVM? But having said that, the SVM is still widely perceived as one of the most powerful learning algorithms, and there is this regime of when there's a very effective way to learn complex non-linear functions. And so I actually, together with logistic regression, neural networks, SVMs, using those three learning algorithms, you're actually, I think, very well positioned to build state-of-the-art, machine learning systems for a wide range of applications. And this is another very powerful tool to have in your arsenal, one that is used all over the place in Silicon Valley or in industry and in academia to build many high-performance machine learning systems.